Next, we'll work on joint and conditional Gaussian random variables, and we'll end up with the fundamental equations of linear estimation, as we'll see in a short while. We say that two random vectors, x and z, are jointly Gaussian distributed if we set up a stacked vector y, first x, below it z, so they are one on top of each other, if this stacked vector is Gaussian, namely the joint density of x and z, which is the PDF of y, is Gaussian with argument y, mean y bar, and covariance matrix p sub y. Now, the mean and covariance matrix are as follows. Y bar is just the stacked vector consisting of x bar and z bar, and pyy is a matrix with blocks. The first block, top left, is the pxx, which is the covariance of x, e of x minus x bar times x minus x bar transpose. The second block is the covariance of z. We denote again x with itself, z with itself, and the off-diagonal block, pxz, is the covariance between x and z, e x minus x bar, z minus z bar transposed, which is the transpose of pzx, because then we have to take them in the opposite order. So, with these blocks, we have the partitioned version of the covariance matrix of this stacked vector y. Now, what we are looking for at this point is the conditional density of the first, that's x, given the second, z, when they are jointly Gaussian. And px given z is, according to the definition of the conditional probability density function, the joint density of x and z divided by the density of z. So pxz over pz. And notice that pxz is the same as p of y, so we write it as p of y here. And we have in the exponent the quadratic form y minus y bar transpose pyy inverse y minus y bar. And in the denominator, we'll have the p of z, and this has a quadratic form in the exponent z minus z bar transpose pzz inverse z minus z bar. Now, what we are going to do is take advantage of the fact that we have the ratio of two exponentials, which ends up requiring the difference of the two exponents. And with this, we'll be able to simplify the final equation. Note there's two normalizing constants in front of that, each exponential that right now we don't care about. Okay, the result will be again a quadratic form in x, meaning that the conditional PDF of x given z is also Gaussian. And there is algebra, which we skipped here, and please review the detailed derivations in the textbook. So, what we have is that the ratio of those two exponentials using the so-called completion of the squares in the matrix version, this completion of the quadratic forms, and manipulation of those terms will give us that the conditional density of x given z is quadratic in x. Namely, we have a quadratic form that says that x given z is Gaussian, and we will recognize the mean of x given z, that we denote as x hat as x bar, this is the unconditional mean, plus the covariance between x and z times the inverse of the covariance of z times z minus z bar, and there is a covariance in this quadratic form in the conditional density, which is the covariance of x given z, that is denoted as pxx given z, and this is one of the blocks that we have in the inversion. Actually here, the detailed manipulations that you should follow from the text take advantage of the inverse of the partition of a partitioned matrix, namely the partitions of the inverse can be related to the partitions of the original matrix, and we end up with this pxx given z as pxx minus pxz, pzz inverse pzx. The first observation is that the conditional mean we have here is linear in the observation z. So we have the unconditional mean, and to this we add a linear function of z. And the covariance, which is in this second equation, conditional covariance is unconditional covariance minus, this is the covariance between x and z, pzz inverse, then pzx. You can see that it's a nice symmetric form, the way it should be. Furthermore, it is independent of the observation. Namely, the covariance of x conditioned on z can be calculated without need to know what will be the value of z. And these are the fundamental equations of linear estimation. And we'll see that later when we'll do least squares estimation, we'll do the Kalman filter, all have forms very similar to this fundamental equation. Another item of interest is what is called chi-square distributed random variables, which are defined as follows. If we start with an n-dimensional random vector x, which is Gaussian, its mean is x bar, its covariance is p, then the scalar random variable defined by a quadratic form, which is x minus x bar transpose p inverse x minus x bar. So this expression denoted by q, which is, by the way, is the same expression that appears in the exponent of the Gaussian density. This can be shown algebraically to be the sum of the squares of n independent, zero mean, unity variance Gaussian random variables, and that's what's called standard Gaussians. Such a random variable is said to have a chi-square distribution with n degrees of freedom. The meaning of degrees of freedom will become clear later when we discuss least squares. So, take a single Gaussian, square it, divide it by its covariance after you subtracted the mean from it, and by its variance. If it's a scalar, you end up with a chi-square with 1 degree of freedom. Write a quadratic form of an n vector that is Gaussian by subtracting the mean and taking the quadratic form with respect to the covariance matrix of this random variable. You end up with an n degrees of freedom chi-square. Next topic will be random processes. We have seen random variables. A scalar random variable is a real number x determined by the outcome omega of some random experiment. So x is function of omega. Now, a random process or a stochastic process is a function of time determined by the outcome of a random experiment. Now we have x of t is x of t and omega, as opposed to just a value, x of omega. So what we have is a family or an ensemble of functions of time, which in general would be different for each outcome omega. First thing we are interested is moments. The mean or ensemble average is another term for it. For a random process, x of t is the expected value of x of t, denoted in shorthand by x bar of t, which will be the integral on all the possible values xi p of x of t at xi d xi. So this is now the probability density function of the value of the random process at time t. The autocorrelation is defined for a real valued scalar process as e of x at t1 times x at t2. Here we deal with a single point in time, here we deal with deal with 2 points in time and define a second order moment denoted as r at arguments t1, t2. And this will be the double integral psi eta, the joint probability density functions of the values of the process at t1 and at t2 at psi and eta, and integral over psi and eta. This is a non-central second moment. We have a central second moment in this case. Autocovariance of this random process is denoted as v at t1 and t2. The expected value of x, again this is a scalar process right now, so there's no need for worrying about vectors yet, x t1 minus x bar t1, so subtract the mean and multiply with the x t2 minus x bar t2. As you see, just take off the means, so we have a central moment, and this is r t1 t2 minus x bar t1 x bar t2. I suggest to go through the small derivation connecting the first line to the second line by just opening the outside brackets here. It's called autocovariance because it's the process xt with itself. That's why auto. Later we can see cross covariances between one process, say x of t, and another process z of t. So we have autocorrelation, non-center second moment, autocovariance, center second moment of a process with itself. When needed, we'll use subscripts here. Right now there's no need. So we have the terminology problem that the autocorrelation is now an unnormalized and non-central moment. We don't subtract the mean. While in the case of random variables, we use the term correlation for a normalized joint central moment. It should be also added that if the process is zero mean, the distinction between central and non-central moment disappears. Obviously, there's no mean to subtract when it's zero. But it's important to remember that the autocorrelation is a non-central, unnormalized, as opposed to correlation, which is a central and normalized second moment for the random variable situation. So there's a slight ambiguity in terminology, but it is so accepted that we will follow it from now on. Stationarity. We can talk about a random process whose mean is time invariant and whose autocorrelation has the following form. RT1, T2 is really a function of only the difference between these two time points, as then can be denoted this difference by a tau. So instead of having really two arguments, it has a single argument. Namely, the first two moments are invariant with respect to a shift of the time axis. If the mean doesn't depend on the time, it doesn't matter where the reference is. If the second moment, which has in general two time arguments, depends only on the difference between those two time arguments, again a shift in the time axis makes no difference because it would cancel out. This process now, if it has these two properties, is called white sense stationary, or less rigorously stationary. The strict stationarity would require that the probability density function of the process at a point in time and at 2 points in time would be invariant with respect to shift of time. Here, the white sense requirement refers to first and second moments as opposed to probability density functions. Another important issue is for a real valued process, the autocorrelation is symmetric in its two time arguments. RT1 T2 is RT2 T1 because the product that we take is commutative. When we talk about complex random processes, one will be the conjugate of the other one because the autocorrelation is the first times the conjugate of the second one, but this is typically used in signal processing. In this course, we are not going to need it, but it's good for you to be aware of it. So, for a real-valued process, R, if it's stationary, is a function of a single time argument, and it's a symmetric, an even function. R of tau is the same as R of minus tau. It is well known that frequency domain approaches are very helpful in providing shortcuts in a number of problems. So we have the power spectrum or power spectral density of a stationary random process defined as the Fourier transform denoted by script f of its autocorrelation function. So S of omega is the Fourier transform of R of tau. So that's integral e to the minus j omega tau r tau d tau, and omega is the angular frequency. And here is the comment I just made earlier, that strict stationarity requires that all the probability density functions to be invariant with respect to time shift. In practice, White-Stand stationarity is all one can assume for and really hope for, because it's very hard to have probability density functions for a random process. Let's take an example. We'll take a scalar dynamic system with equation x dot minus axt plus nt with a positive a, namely it has a in continuous time a negative eigenvalue. So what we have here, a negative left half plane pole, and that's in the transfer function domain. So it's a stable system. That's very important. The input n is a zero mean white noise with autocorrelation, because it's zero mean does the same thing as the autocovariance. E of n at t1 times n at t2, so that's the noise here, the driving noise, is a constant times a Dirac impulse delta function, argument t1 minus t2. So this is an impulse function, and S is the intensity. We'll see its meaning in a moment. If the system is in steady state, namely the initial condition died out, we can obtain the response of this system to the input noise driving function n of tau as the integral of the product of the impulse response ht tau n tau d tau. This impulse response for the above system is e to the minus a t minus tau. So if the pulse comes in at time tau, the input comes in at impulse response. If there's an impulse comes in at tau, the output at t is given by this function. Now, the mean of the output is the first thing we'll consider, is the expected value of xt, is the expected value of the integral from minus infinity to t, ht n tau d tau. And remember that expectation is an integral, and we have a time integral, and that's really with respect to probability density function. So these two integrals can be interchanged under the condition that both are finite, that both integrals converge. So we bring the expectation inside the integral with respect to time, and we have integral ht tau e of n tau d tau equal to 0, because the expected value of the noise in the integrand is 0. So we are done with the mean of the output, 0 mean input, 0 mean output. And again, that's assuming there's no more transient, the initial conditions die out by now. The autocorrelation of xt would be the expected value of x at t1 times x at t2. So we have two integrals here. This is the x at t1, there's integral h t1 tau 1 n tau 1 d tau 1, and d tau 1 is the dummy argument of our integration. Here we use a different dummy argument d tau 2, and this is n tau 2 d tau 2 multiplied by h t2 n tau 2, and this is integrated from minus infinity to time t2. So these are the two responses. Now, we have to assume which is larger of the two times T1 and T2. Let's assume right now T2 is the larger one. Then we can write the expected value of this product as the first one, this is xt1. The second, the expression in the brackets, is the part of xt2 up to time t1, the contribution to xt2 of this input n up to time t1 plus its contribution from t1 to t2. So we broke down the second integral as into the sum of two integrals. Now, in view of the fact that the first and last integral above are over non-overlapping interval, this was the purpose of decomposing the second integral into two parts, the expected value of their product will be 0 due to the fact that nt, which we'll see, we'll call it white noise, has autocorrelation that is 0 at any two different times. Remember, its autocorrelation was a Dirac delta function, which means it's 0 at any two different times. Therefore, for non-overlapping integrals, the product after expectation will give 0. Now, the expected value of the xt1 times xt2 is the first integral plus the first part of the second integral. Now, remember, here we have a t1, here we have a t2. We'll want to have both of them the same, so we'll multiply it with an e to the at1 minus at2. Then I have here another minus 81. So with this, we have these two integrals really the same. They're just dummy variables, tau1 and tau2, each yield x at t1. So this is the expected value of x at t1 squared. So you can see that the autocorrelation of the process is the instantaneous mean square value times e to the a t1 minus t2, and this is a negative quantity because t2 is larger than t1, and we can use the other assumption. If t1 greater than t2, we have the same thing except t1 and t2 are switched. Therefore, the expected value of x at t1 times x at t2 is e to the minus a times the magnitude of t1 minus t2 times the mean square value, the instantaneous mean square value of the process at time t1. So the autocorrelation decreases exponentially from its peak, which is the steady state mean square value of xt or its instantaneous power. Just like voltage squared is proportional to the power we will call by convention the square of a variable its power, and this is the mean square value because this is a random process. Then its power is the mean square value of this function x of t. Now, how much is this? We don't have it yet. So we'll calculate that integral. The expected value of xt, now we don't need a t1 or t2, just a generic t, is the expected value. This is the output. This is the impulse response function, nt1 theta 1, and the same thing with the dummy second argument, tau 2, with the upper limits of both integrals being the same common t here. So the expected value of this double integral is the double integral, and we pass the expectation all the way inside to the product of n tau 1 and n tau 2. There's nothing else random here except the two n tau 1 and n tau 2. And what we have now, this expected value is the constant S0 times the delta function. So we have a double integral, e to minus 2at can be pulled out, and we have now the double integral with respect to tau 1 and tau 2 because of the delta function becomes a single integral, namely the delta function's sampling property. The integral with respect to tau 2 is the value of the rest at tau 2 equal to tau 1. So we have a single integral, S0 is constant, goes out, tau 2 is replaced by tau 1, so e to the 2a tau 1 d tau 1, which can be integrated from minus infinity to plus infinity very easily and gives us S0 over 2a. So this is now the expression of the mean square value of the process xt, or its average power. Therefore, the autocorrelation is between 2 points in time. We change the notation from t1, t2 to a t and t plus tau, is S0 over 2a, that's the instantaneous average power, times e to the minus a magnitude of tau. And you can see again it's symmetric. For tau positive or negative, you get the same thing. So this is now the result of the autocorrelation of a linear dynamic system driven by white noise. It's a scalar system at this point. Now we can go and take the Fourier transform of the above, and we'll use the notation of the unit step function to rewrite an exponential. Because we have a two-sided exponential, we need one expression for the negative values of tau and one expression for the positive values of tau. So the Fourier transform, the script f of rxx of tau, will give us sxx omega, and again the subscript xx means autocorrelation, x with itself, and each exponential for the left hand side and for the right hand side give us 1 over a minus j omega, the other one 1 over a plus j omega. Add up the two, end up with S0 times 1 over a square plus omega square. So what we have is a stable first order system, and you can see this is really a low pass filter transfer function. So its effect on the spectrum of the input, which being a white noise, we'll see it in a moment again, has a flat spectrum, will attenuate the high frequency. So this is what a first order system, stable system does, attenuates the high frequencies. Another property that we would like to bring in is ergodicity. If you have a stationary random process, we say it is ergodic, then time averages of some functions of the process are equal to the corresponding expected values or statistical averages or ensemble averages, namely the time average of this function, 1 over 2t integral from minus to plus t xt dt will be as t goes to infinity, the long-term average over time the same as the ensemble or statistical averages. Now, this is very important in the real-time performance monitoring of state estimation filters, because sometimes you have only one single realization of a random process, but you can look at it for a long time and you take advantage of the ergodicity, do a time average which can be substituted based on this property ergodicity for the ensemble or the statistical average. Now let's go back to the white noise. You can have a random process, not necessarily stationary, whose autocovariance is 0 at any two different times, is called white noise. Here's the autocovariance. V at t1, t2 is some expression times delta t1, t2 is S0 t1 times delta t1 minus t2. So what we have here is a delta function at any 2 points in time, t1 and t2 different. The autocovariance is 0. Now, sigma square t1 is called sometimes, not quite correct, the instantaneous variance. This is the white sense whiteness as opposed to the strict sense whiteness. White sense whiteness means up to second order term it is white. means second moment. The autocovariance is 0 at any two different points in time. The strict sense whiteness says not just uncorrelatedness, but full independence at two different points in time. Also, it's important to point out that what you have is the fact that when you take the Fourier transform of the white noise, delta function's Fourier transform is unity. Therefore, its Fourier transform, if it has a constant S0 here, is that constant S0. Means the spectrum is flat. And this is the physical counterpart of what we call white light, which has a spectrum that is flat, at least within our visible region, and this is why this is called white noise. Now, a stationary zero-mean white process has this autocorrelation. R of tau, E xt plus tau xt, which is S0 delta of tau. So that's the delta function. And that's what just mentioned a moment ago. When you take the Fourier transform, the power spectral density is this constant S0, because the Fourier transform of the delta function is unity, and it's a constant across the frequency spectrum, entire, from 0 to infinity frequency. Obviously, this is an idealized situation. Nevertheless, in our physical modeling, it's very successful for the following reason. All systems really don't care about very, very high frequencies. So practically, white noise is practically a noise is white if its frequency spectrum is flat over a wide enough range up to high enough frequency beyond the maximum, the cutoff frequency of a physical system we deal with. And this really provides us a very simple modeling of this particular random process. Okay, a non-stationary zero-mean white process, E of xt1, xt2 is some S0 T1 delta T1 minus T2. And the S0 of t can be used with some abuse of language as time-varying spectral density. However, the term instantaneous variance that was indicated before is really incorrect, because the variance is actually infinite. You can look the variance, given that it is zero mean, is this whole thing. So S0 is really not the variance, is the power spectral density multiplied by the delta function would be the variance. So the physical dimension of the quantity sigma square in the previous equation, or of S0, is really the square of the dimension of x. This is the square of the dimension of x multiplied by time. You put a delta, physical dimension only, it's to the left-hand side is 1 over delta, which is time, because the impulse function has as dimension the inverse of time. Remember, integral of delta t dt is 1. Therefore, delta has a physical dimension of the inverse of time. So this is why using the term instantaneous variance is not a good idea. Okay, a note on whiteness. When a result in the future requires whiteness, it is usually strict sense whiteness, namely the random variable xt1 and xt2, the values of the random process at two different times, these random variables, are independent. But typically what we have is uncorrelatedness, which means white sense whiteness. And while this is only approximately true in theory, it is in our experience good enough for engineering purposes. Now, here is a very important random process called the Wiener process, or random walk. The Wiener random process, or Wiener-Levy or Brownian motion is a limiting form of the random walk, namely the sum of independent steps of size s, which goes at the limit to 0, equiprobable in each direction, plus or minus s to the left or right on the real line, taken at intervals delta going to 0, such that the ratio between the step size s and the square root of the interval of time at which a step is taken goes to a constant denoted as square root of alpha. Now, this yields a stochastic process w of t with the following probability density function, assuming it starts at the origin at time 0. Probability density function of w of t is Gaussian, argument is w of t, mean is 0, variance is alpha t. Now, this is a non-stationary process because you can see immediately that its variance depends on time. So, second moments are not going to be invariant with respect to a shift of the time axis. In addition to being non-stationary, it's interesting to see how it relates to a zero mean white noise that we denote as NT. Specifically, W of t, this process, is the integral from 0 to t of a zero mean white noise, n of tau, d tau, where, being white, the autocorrelation of this, or autocovariance, because we said it's zero mean, is alpha times a delta Dirac delta function, delta of t1 minus t2. You can go back to this integral and look at its differential form. The increment w, dw of t, is nt dt. Now, n is white, therefore it is uncorrelated at any 2 points of time. If we go to the strict requirement, strict whiteness, we say it's independent at any 2 points in time. So what we have, the increment of the Wiener process is independent over different time intervals. So we have what is called an independent increment process. So that's a very important property of the Wiener process. And we'll see how we can model certain physical quantities either by white noise or by Wiener process. This is why we stress their properties. Now, the Wiener process has the following autocorrelation. Again, proof is in the text. The expected value of WT1 times WT2 is alpha times the smaller, the minimum of the two quantities, two values of time, T1 and T2. The place where we use white noise and Wiener process to model unknown inputs in state estimation and interacting, because we don't know certain inputs, we will model our ignorance by some statistically described process. It's important to remember that since the Wiener process is really not stationary, it does not have a power spectral density. It has an intensity that will be time varying.